In this section, we're going to talk about vectors in space. And so what I mean by that is we are now going to start thinking about things in 3 dimensions. And in fact, that's what we're going to be doing throughout this semester in this class. In your previous math classes, you typically worked with 2 variables. You had an input, which you usually called x, an output, which you called y, and you would graph things in a 2-dimensional plane with an x-axis and a y-axis. And now all of a sudden we're going to start to think about things in 3 dimensions. And so our rectangular coordinate system now is going to have 3 axes. We're going to have an x, a y, and a z-axis. And so it's a 3-dimensional coordinate system. A nice way of kind of visualizing what I've tried to draw on the screen is if you're in a room and you just look at a corner, you see kind of 3 lines meeting together in that corner of your room. You can think of that as our 3 axes. We're going to describe our points now as ordered triples instead of ordered pairs. So we'll always list the x, the y, and then the z coordinate. Let's see, a little bit of vocabulary. What I've tried to shade in yellow, it is called the xy plane. That's a place where z is always equal to 0. Or we could say that's the plane z equals 0. We might also talk about what we call the xz plane. So that's a place where the y values are always 0, or the plane y equals 0. And then finally we've got the yz plane, which is where x equals 0. Sometimes these are called our coordinate planes, connecting the axes. All right, so let's plot a point and try to find its distance to the origin. So I'm going to plot the point 3, 5, 2. So let's see, x is 3, y is 5. So I've kind of tried to sketch in yellow what I'm thinking right now. So over 3 on the x, over 5 on the y-axis, and then I have to, from that location, go up 2. And so I kind of sketched a box to kind of illustrate what's happening here. So from that point in the xy plane, from the point 3, 5 in the xy plane, I just went up 2. And so in blue, that would be my point. The region where this point is, one more kind of vocabulary word for you. Because the x, the y, and the z are all positive, I would say that this point is located in what we call the first octant. So our 3-dimensional coordinate system actually divides space up into 8 sectors. And so we call this the first octant, where everything is positive. All right, so what about the distance? Let's see if we can find the distance from the origin to that point, which I've drawn in blue. And so we are trying to find basically the length. Let me highlight it. I'm trying to find this length right here. That's the distance we're trying to find. And I noticed that I can draw a right triangle kind of sitting up on that xy plane. And let me just draw a side view of that triangle. So I've got this little triangle here in purple I'm going to use to find that distance. So again, I'm trying to find this distance d. That's the distance from the origin to the point. All right, the height of this triangle that I've drawn in purple is my z coordinate. In this case, it's 2. But the height, I'm just going to label that z for now. The bottom, though, the base of that triangle, I'm not quite sure what that is quite yet. And so I'm actually going to draw a second triangle. I put it in blue. And I'm going to see if I can figure out what is the length of, I've drawn it in red now. So I'm trying to find this distance here. put it in red, which corresponds to this length on the xy plane. And that happens to be the hypotenuse of the triangle that I drew in blue. And that triangle has a base which corresponds to the x-coordinate. In this case, it's 3. We went over 3. And then the height of that triangle corresponds to the y value. Let's see, 5 in this case. So focusing on that triangle in blue, the one in the xy plane, we can find the length of the hypotenuse by using my Pythagorean formula. So in this case, x squared plus y squared has to equal hypotenuse squared. So the length of that hypotenuse would be the square root of x squared plus y squared. And then back to the triangle in purple, the original problem, what is that distance d? Well, that's another right triangle. So let's just use our Pythagorean formula again. So we'll take our square root of x squared plus y squared squared plus z squared, and that's going to equal our distance squared. I'm going to do a little bit of simplifying. Squaring a square root gets rid of the square root. So now I've got distance squared is x squared plus y squared plus z squared, or distance is the square root of the sum of those squares. And so finally, in this problem, we actually have numbers to work with. Let's just put those numbers in. Our x distance is 3, y is 5, z is 2. So plugging all of that in, square root of 9 plus 25 plus 4, I got square root of 38. So that's the distance from the origin to that point. And in fact, we can generalize this, and here's my distance formula in 3 dimensions. If we want to find the distance between 2 points in space, we're going to take the square root of our change in x squared plus change in y squared plus change in z squared. So really similar to our distance formula in 2D, just got that extra kind of z squared in there. Let's do another example. Let's try to write the equation of a plane. So plane is, it's like a two-dimensional version of a line. It's kind of like a piece of paper, something that goes on forever in both directions. So let's write the equation of a plane that passes through the point 2, 1, 4 that is parallel to the xz plane. So I'm going to start by just kind of thinking about where is that point 2, 1, 4. So x is 2, y is 1, z is 4. And then I want to draw something that is parallel to my xz plane. And so this is my xz plane. So something that is parallel in the same direction as that xz plane. So something that kind of looks like this. And so if I'm drawing something that's parallel to the xz plane, it's the y values that are always constant. The y values are always the same. And based on where that point is, if it's going to go through the point 2, 1, 4, that has a y value of 1. And so my plane always has y values of 1. And we can just write that equation as y equals 1. All right, the other type of equation I want to show you right now, and we will talk about more equations of surfaces, but I want to focus on just some kind of simple equations in this video, and we'll expand on these ideas later on. So on the screen I have the equation of a sphere with a center at A, B, C, and a radius of R. This should look really similar to the equation of a circle. We just have that z term in there. And it comes from our distance formula in 3 dimensions. The idea that the distance between every point on the sphere and the center is always equal to that radius r. So here's an example. Let's see if we can graph x squared plus y squared plus z squared equals 9. And so first thing I recognize is this is a sphere because it's an x squared plus y squared plus z squared. I know that the center is located at the origin because there's nothing with the x, the y, the z, the squared quantities. R squared equals 9, so the radius of this sphere has to equal 3. So what we have is a sphere or a ball, radius of 3, centered at the origin. So I'm going to try to sketch that in my coordinate system. And so when I'm drawing pictures of things in 3 dimensions on a 2-dimensional piece of paper, I usually start by trying to draw what I think it would look like in the XY plane. It gives me kind of a good starting point. And then it's going to go up 3 and down 3 from that center as well. And so I'll try to draw something that looks like a ball, goes up to z equals 3, down to z equals negative 3. All right, next example. Example 4 says a sphere has the points 2, 1, 0 and negative 4, 3, 6 as endpoints of a diameter. Let's write its equation. So first of all, the center of the sphere is going to be the midpoint of that diameter. A lot like with circles. The center of a circle is the midpoint of the diameter, or halfway between those endpoints on the diameter. So to find the midpoint of that diameter, I just have to take the average of the endpoints. So add them together, divide by 2. So the x value of the center is going to be located at, I'm going to take 2 plus negative 4 divided by 2. And then for the y value of the center, I'll do 1 plus 3 divided by 2. And then for the z value, 0 plus 6 divided by 2. So that gives me a center located at negative 1, 2, and 3. And that, again, that's a point that's located exactly halfway between those two endpoints on the diameter. So I know where the center is. And then I do need to know the radius. And so the radius of this sphere is going to be the distance from the center to either one of those endpoints. I just randomly am choosing to work with the first one, 2, 1, 0. But I should get the same distance from the center to the other endpoint as well. So I'm just going to pick one endpoint and then compare it to the center and find the distance using my 3-dimensional distance formula. So the radius is going to be the square root of my change in x squared. Okay, so I didn't really show all my work here. So my change in x is 2 minus negative 1, that gave me 3. And then my change in y is going to be 1 minus 2, that's where the negative 1 came from. And then the change in z, 0 minus 3, that's where the negative 3 came from. So I'm going to take my change in x squared plus change in y squared plus change in z squared, and that gives me square root of 19. So there's my radius. I have my center. Plugging that into my formula gives me my answer. The equation of this sphere is going to be x plus 1 squared plus y minus 2 squared plus z minus 3 squared equals square root of 19 squared. I'll just call that 19. All right, finally, what I want to focus on in kind of the second half of this video is thinking about vectors in 3 dimensions. And so in section 2.1, we did a quick overview or a brief overview of working with vectors, which are directed line segments or arrows in 2 dimensions. I want to now just expand all of those ideas to 3 dimensions. So we can have vectors in space in 3 dimensions. And that means our vectors are going to have 3 components: an x component, a y component, and now we're adding this z component as well. And so we can write our vectors in component form with those kind of triangular brackets, or we can write them with i's and j's, and then we're going to add this kind of new unit vector k to describe what's happening in the z direction. The magnitude of the vector, if you remember from the last video, we were basically using our distance formula or a Pythagorean formula to find the magnitude of the vector. And so using my 3-dimensional distance formula, the magnitude of that vector is going to be the square root of the sum of the squares of the components. And again, that really is just my distance formula. I'm taking my change in x squared plus change in y squared plus change in z squared. I'm just thinking of those quantities as components of a vector. Okay, so the new part here is we have this third z component of our vectors that we're going to have to deal with. But otherwise, the math that we learned in the previous section applies. If we want to add or subtract vectors, we add or subtract the corresponding components. If we want to take a vector and multiply it by a scalar, we just distribute the scalar to each component. So same kind of properties that we learned in the previous section apply here. So if I have a vector with an initial point at -2, 3, 1, and a terminal point at 0, 4, -4, and I want to find 3 times that vector v minus 2 times k, well, the first thing I'm going to do is figure out what vector v is, and I can do that by taking the terminal point minus the initial point. So my x component, 0 minus -2 is 2, the y component, 4 minus 3 is 1, and the z component, -4 minus 1 is -5. So there's vector v in component form, 2, 1, -5. All right, and then I am going to take 3 times vector v minus 2 times vector k, and k is this new kind of standard unit vector. It's the vector 0, 0, 1, so it just points in the z direction. That's always going to be vector k. And so I'm going to distribute the 3 to vector v. I get 6, 3, -15. And then I'm going to subtract 0, 0, 2. And that gives me 6, 3, -17. Okay, part B is asking us to find a unit vector in the direction of vector v. And so in the last section, we learned a unit vector is a vector that has a magnitude of 1. And so the way to do this, same process we used in the previous section, we're going to find the magnitude of vector v. So we're going to take the square root of the sum of its components squared. So square root of 2 squared plus 1 squared plus -5 squared. I got root 30. So the magnitude of vector v is square root of 30. And then we can just take vector v and divide it by square root of 30. And that's going to be dividing each component by square root of 30. And now we have a new vector, same direction, but with a magnitude of 1. So my unit vector is 2 over root 30, 1 over root 30, -5 over root 30. Let's see, finally I've got one more example I want to run through. Example 6, are the 3 points collinear? So we've got point A is 4, -2, 7, point B, -2, 0, 3, and point C is 7, -3, 9. So first of all, are these points collinear? That word just means, do they lie on the same line? So if I were to graph them Do they all lie on the same line? There's several ways to answer this question, but I'm going to answer this question using the concept of parallel vectors. So parallel vectors point in the same direction. I guess they could point in opposite directions if one of them is a negative and one is positive, but the idea is they're tilted the exact same way. Kind of like parallel lines have the same slope. And so parallel vectors are always scalar multiples of each other, so just multiples of each other. So if these 3 points lie on the same line, if I create a vector from A to B, and then from that same starting point A to C, those two vectors have to be parallel, or scalar multiples, if the 3 points all lie on the same line. So I'm going to compute vector AB and vector AC. I'm going to take my terminal point minus my initial point. So vector AB turns into -6, 2, -4. And then for vector AC, again, terminal point, which was C, minus initial point A, gives me 3, -1, 2. And I can see by looking at these two vectors that they are just multiples of each other. If I take vector AC and I multiply it by -2, that does give me vector AB. If I take each of those components in AC and multiply it by -2, I get -6, 2, -4, which it was vector AB. So because these vectors are scalar multiples of each other, they're parallel, and therefore these points are collinear. They all lie on the same line. All right, that was my last example in this video. As always, let me know if you have any questions.